Ujigan visiting us today. So he is one of the most active researchers in algorithms community and has done a lot of good work. So one particular line that I find very inspiring is that he keeps building a theory for graph decomposition to design fast graph algorithms and dynamic algorithms. So today he will talk about something else.
Yes. Yeah. Thanks a lot for inviting and great to be here. So I'm very happy to talk about graph decomposition for the data graph. Today is something else, but I hope it's still interesting. Okay. So this is based on joint work with Petty and Long Wei. But like there are several things in the paper. We're gonna focus on one aspect in that paper, which I find interesting. So which is about hardness of approximation. It's about gap amplification. Yeah. And we're gonna see space lower bound for basic graph problems. Okay. So let me start with some story about like that to motivate this. Okay. So the problem that we're gonna look at in this talk is Maxwell oracle. So the problem is just you have a graph with n nodes. Just you have a graph and you want to pre-process this graph and build some data structure. So the goal is to get the data structure such that now given any node U and V, you can return a Maxwell value from U to V. That's the problem. The question is just how much space does this oracle, this data structure take? Okay, that's just a basic question like this. Okay. And now, clearly when the graph is directed, then you need n square space. Okay. So let's see why. Let's consider the graph that is directed. Okay. It's directed by bipartite graph, like here. There are n nodes here, n nodes here. And you can see that if you look at any pair of nodes, U and V, then this max flow is going to be from U to V. It's going to be 1 if there is an edge from U to V and 0 otherwise. So basically the max flow value encode whether there is an edge or not for each pair. So just by querying all pairs U and V, then you can reconstruct the graph. So but there are so many graphs, right? Like you basically encode n square bits of like n square bits. So this data structure would need to spend n square space. So that you can count to like there are this many possible graphs. So one of the graph means this many bits. So okay, n square space for the data graph, that's kind of clear. On the other hand, if the graph is undirected, then it turns out that it's like a really great structure and you can get n space. And that is the Gomorin-Hood tree. So Gomorin-Hood tree, informally, is just kind of a tree that can encode every ST max flow for every pair. So this is a graph, and then you can construct another tree that basically encodes all max flow value. I will not define it explicitly, but let's see one example. Suppose that you want to compute max flow from A to T. Okay. Then you can look at the node A and T. And then you just ask like what's the max flow from what's the max flow value from A to T in the tree, in this tree. And then you consider there is only one path from A to T. That's the only way to send flow. And so the max flow value is going to be bottleneck at 4. So that's going to be max flow value on this tree. And it's going to be the case that max flow value in the graph is also 4. And moreover, if you look at the cut, like this is a bottleneck edge. If you cut this edge, it will separate the graph into two parts. The graph, it will separate these three into two parts. It's going to be the case too that the mean cut, this is going to be the mean cut too in the graph. This is going to be true for every pair. So it's a good and nice structure. I will not talk about this today, but under the graph, you have this tree, and this tree has n-1 edge. So you need like a n log n bits or something. So it's nice. Yeah. So there is this dichotomy between the related graph and undirected. Yep.
Reminds that what if one was short bound, is it n log n? Is there an n log n lower bound for this?
Good question. I haven't think about this before. Yeah. Can we get n or n log n is enough? I don't know. Yeah. Or n log n is required or not? I don't know. Good question.
So n log n equal to what?
Like is the lower bound for the problem n log n bits of a space or n bits?
Right. Right. Let's see.
The fact that max flow encodes connectivity, what boundary get lower bound is it n or n log n?
I think just connectivity, you might get n. I am not sure, but actually I see the low bound of n log n now. I'll tell you later. Maybe like you have a meshing. And this you can encode some number from 1 to n. Like, yeah, some number. You can encode n many numbers. Yeah. Okay. Okay, this seems like we are done, like we good. But this structure is for edge capacity. It's for edge cuts. Like this is the cut of size 4, and this like a cut of size 4. But it's like the cut where you count the size of edge, total size of edge. So we can ask another natural question, which is vertex cut. It's just as natural as edge cut, like yeah. So some basic fact about vertex capacity, right? Max flow with vertex capacity is the same as minimum edge cut. So now max flow with vertex capacity is the same as minimum vertex cut. Okay. It's a natural question. For example, you have S&T, instead of asking how many edge disjoint parts are there, you can ask how many vertex disjoint parts are there. So it's just a question since the 70s that is there something like a Morin tree for vertex capacity, for a graph for vertex cut in undirected graph? Okay, so that's a question we want to study, and here's a fun history. So, okay, then like in the 90s, Gasfield and Naur show this. They show that, okay, actually there is one Morin tree for vertex cut. So that takes n space, n log n bits. But then 5 years later, Ben shows that this is actually, there is a counterexample of his claim. It's not quite correct. He instead showed that, okay, there is something else, relaxation, something called flow tree for vertex cut. It's weaker, but still encodes all pair max flow. And then like 10 years later, Hassin and Levin shows that this is wrong too. There is a counterexample for this claim. But what he shows is this. He shows that actually there is a graph such that there are n square, many distinct vertex max flow value. So there is a graph such that the different value of vertex max flow is n squared. If you look at like all pairs, they kind of contribute different value most of the pairs.
Capacitated.
This is capacitated. Good. Yeah. This is capacitated graph. So what does this rule out? It rules out that there cannot be a tree of linear size. Okay. Because if you have a tree of linear size, the tree has linear size. It has just n size. It has n many possible cuts, n many possible min cuts. So you cannot get a tree of even like less than n squared size to represent all pair max flow with vertex capacity.
So in this version of Maxwell, vertices have capacity?
Yeah, vertex
The
has
edges don't
capacity.
have-
Second,
The edges don't have capacity?
yeah, edge. Let's say edge has capacity infinite. You can just like you can say, for example, you have S and T. In the unit capacity case, you ask how many nodes you need to delete to disconnect S and T. Okay.
Very hard on parsing this, a tree cannot have that many edges anyway. So are you saying there's no data structure of this?
Yeah, maybe you can construct a tree with like that make many copies or add standard nodes. Like just add more nodes of this stuff so that you have more like you start with a graph with n nodes. Maybe you get a tree of more nodes.
Okay, but wouldn't that sentence just imply that there's no data structure of size as small of and a square?
Not quite, because it could be that like the data structure is of size small. Like think like Gomori tree. No, wait, sorry. There can be some data structure that have small size, but it can encode many numbers. Let's say, for example, like you have a list of n numbers, and then I can add these numbers together. Yeah, it can generate many different numbers still.
Third question I had, like in Gomani tree, basically if you're measuring like flow from one vertex to the other, you're like summing up stuff. So I don't know how the first sentence that n squared distinct values are there, rules out some kind of tree of size and pointing out.
It will rule out. Let's say for now that it will rule out something like a vertical tree exactly. We're gonna rule out something very like much more stronger anyway.
But is there, why couldn't we have n squared different values in variable tree?
Oh, because
Do sums and stuff like that?
because good. When no, it's good. Because in Gomori tree, when you fix one pair of nodes, there is always just like I mean cut is always just one edge. It's always just mean cut in tree is always one edge.
Okay.
So if you have like n edges, you can just generate only like n many numbers. Good. Okay. Good questions. All right, let's come back to the history. Okay, so now like Hassan and Levin like show that benzoreside is like actually there is a hot example, and here's the thing. This is correct actually. Yeah. So good. Yeah. But the question is this: like this kind of ruled out some really data structure. Can there be like other kind of data structure of linear size? Is it possible? Especially in like when the graph has just unit capacity and natural case. Can that be the case? So this doesn't rule out. This is not ruled out at all. Okay. And what we show is that, okay, you need actually n squared space, even in the unit capacity case. And moreover, even when you have, even when you allow some additive approximation up to root n. Okay. So that's basically clean up the picture now. There is some dichotomy which says that undirected edge cut, you need n size. Now for vertex cut, you need n square.
So that additive approx, suppose you take a bigger thing like, you know, n to the 1 minus epsilon. So in that case, is there any small space data structure? No?
I think something is possible. I don't have I don't know on top of my head how.
Thanks.
Yeah.
And you think about this classifier, just use that.
So this basically shows that there is no cut specifier for vertex cut.
It would not say.
Oh,
But it's n over epsilon a square. Seems to be exactly matching. It's
yeah, n over epsilon square.
and then you get unit capacity or error is epsilon n. Yeah, I'm not sure why not. What is corresponding?
But what's known about cut specifier, it preserves edge cuts, right? We don't have it.
Do the standard tree. Just make. You cannot split a vertex and put an edge of capacity on it.
But then you create like m mini nodes.
No. So this is not a lower bound, it's an upper bound.
Okay,
So
okay.
you give me an undirected graph, I want to preserve its vertex capacity. So I change every vertex by an edge of capacity bond. I still have n vertices, like I have 2 n vertices. I compute the Cotta's falsifier of this graph. The value of ST cot for every pair of vertices less than t will be preserved up to 1 plus epsilon.
So usually the translating a vertex to an edge works in directed.
Yeah, it is directed now. Yeah. Yeah. Good. Okay, good. So like nothing is really so okay, we get the hardness up to root n additive approximation. And here is basically the question that I want to ask. Is there like non-trivial lower bound or upper bound? Even when suppose that you allow now like big additive approximation. Even for the dilated graph. Yeah. So the dilated graph, you have easy lower bound, but that is distinguished between 0 and 1. Can we show this for the dilated graph? That's open. And like maybe like what I want at the end is multiplicative approximation. Yeah. But here basically is a result. And what I want to tell you today, like mainly, I think I want to focus on this thing. Yeah. Because I think
it's approximation actually useful in any way. Like that's such a.
Yeah. So good. Let's see. I don't have application in mind really. Yeah. Yeah. Okay. So now the techniques. Let's see the techniques. Yeah. So what I will show is to actually show this n squared space lower bound for unit capacity case, unweighted case. But let's do it for the dilated case, the dilated graph. Yeah. This is non-trivial already once you talk about additive approximation. Okay. To make it work for undirected vertex capacity, undirected with vertex unit capacity, you do something about graph, which I can tell you later, but I want to focus about this thing. I think it's a cool part in the work. Okay. It's kind of already captured the idea of gap amplification. Okay, so here is a strategy. Here's a kind of too good strategy, but it's rough strategy. So what we do is, let's say that there is some max flow oracle such that given any UNV, it return max flow value up to better than root n, additive approximation. It's like a too good oracle. And what we're gonna say is that suppose that you are given any target matrix, Boolean matrix of size n by n, that encode n square bits. We can construct, there exists some graph with of size O(n) vertices, call it GT. From this matrix, you can construct another graph GT, such that by querying information on, like using this oracle to query on this graph, then you can reconstruct T. So if we can do this, we are done, right? Because then like this matrix can basically encode n square bits. So if you can just given any matrix, you can construct a graph such that by working with this graph using your oracle, you can reconstruct the matrix. Then basically one of the graph must require n square bits. Does it make sense so far? Please ask question, all right? Because yeah, we have time. Yeah. Okay. So this is like what we want to do, but we will not do quite this. What we're gonna do instead is that, okay, we are given a matrix, still a target matrix that we want to encode. And then we're gonna construct another graph, some graph GT, such that when you query, like use this too good oracle to query on the graph, then you can construct almost target. You can construct T tilde, such that the Hamming distance of T tilde and T is basically the same up to 1%. If you can do this, you are done too. Let's see why. Okay. Like I said that if you can do this, you get like for some of the graph, you still need n square bits. Like the oracle must spend n square bit on some of this graph. Why? The short answer is error correcting code. And here's like what I mean. Okay, that actually still exists, like basically 2 to the n square Boolean matrices of this size, right? Such that every pair of matrices in this collection are pairwise far away from each other. How far? Like just pairwise far away by, let's say, almost half of this entry. So it means that suppose that I have a target T, then like target matrix T in this collection, and everything else is kind of far away. T2 is far away, T3 is far away. Now using this oracle, I can kind of obtain some T tilde such that they're kind of close to this T. So basically from T tilde, I know that my original target is T for sure. So basically I can reconstruct my original target T, which encode n square bits. So that's what we want to do. So now the goal is, given any target matrix T, construct a graph such that, like by querying max flow information on this graph GT, I can build this almost target T tilde. Okay. Okay. So now here's a key lemma to achieve this. Given any matrix T, okay, and consider like some large constant C, we're gonna build some other matrix A and B. Okay. A will have the size A times Cn, B will have size Cn times n, and C will be like a product of this A and B. So think of T as like that matrix. A and B looks like that, and C is A times B. I don't tell you yet what is A and B, and here's the property of A and B. I can build matrix A and B such that basically for all entries, it satisfies the following. If an equal ij in T is 1, then if you look at, if this guy is 1, then if you look at this point of C, it's going to be big. Okay? Like bigger than like 10n mod plus root n. Yeah. And if this is 0, then this point is going to be small. Smaller than 10n minus root n. So there is a gap here of root n between the two. This is kind of where the gap amplification is happening. So I can build A and B such that its product is similar to T in this sense. If any entry in T is big, this guy is big. If this is small, like 0, then this is small. But this is true only like on all points except 1%. Okay. Is this statement clear? Okay, then now let's see if I can show this key lemma. Why are we done? Okay, so using this key lemma, we're gonna try to reconstruct T theta, something that is close to target T. So what we're gonna do is like, I'm gonna build now a graph that depends on T. Okay. So given T, I can define A and B. Okay. I tell you that it exists A and B. Okay. From the lemma. And given A and B, A is of size, like given A and B, we can build the 2-layer graph in a natural way. So basically, if entry of I and K, this is of size n, this is Cn, this is n. If an entry from I and K is 1, then you put an edge. If it's 0, if I prime, K prime is 0, then you don't put an edge. The same for B. If this is 1, then you put an edge. If this is K and J, and if the entry of B here is 1, put an edge there. Just a natural 2-layer graph defined by 2 matrices. Okay. So observe that the max flow value from I to J, this is directed graph. I put direction, H with direction. So max flow value from I to J is just the same as the number of parts from I to J in this graph, which is the same as Cij, the product.
Because the capacities are.
Because the capacity is 1. So yeah, good. So let's say that this is my I, this is my J, and let's say that every node has complexity 1, right? So, sorry, actually, let's say that this is, yeah, let's say every node has complexity 1. And now, if I remove these 2 nodes, then I cannot reach J. Yeah. So this is really just to count how many paths from I to J there is. And the number of paths from I to J is just the same as the product from I, like the product of A and B. Look at the entry ij. What's the number? That's, yeah. This is just Cij. So Cij just encodes maximum value between these 2 layers. Okay, so now let me construct T tilde. I'm just gonna define T tilde to be like this. T tilde at entry ij is gonna be 1. If like my oracle returns that the maximum value is more than 10n. And okay, so now I claim now that like this T tilde and T will basically be the same up to 1%. So why is that? Well, because let's say that, okay, let's say that this is T, and then let's say that the first entry here is 1, right? Now, what do we know about this guy? We know that from the premise here, Cij is going to be more than 10n plus root n. So like the number of paths from this guy to this guy is like more than 10n, and even plus root n. But my oracle, okay, it has some additive root n approximation, less than root n approximation. So if this is 1 here, we like the oracle will still report that this is more than 10n because the array is less than root n. Okay. If it's less than 1, if this is 0, then like the number of paths is less than 10n minus root n. So what it will return is still less. It's gonna say that this is less than b. So for any entry such that this holds, you basically can recover what is the, for any entry of T such that that relationship holds, you recover that entry of T, right? But this is wrong only on 1%. Okay. So you're gonna get some matrix T tilde that is wrong on 1% of entries. So you see, like we can construct T tilde that is wrong by 1% as we decide. If I can show that this matrix A and B exists. Good. Okay. So here is the core techniques now, like how to build this A and B. Yeah. Question?
No.
Okay. Yeah. All right. Okay, so this is again what we want, right? Given any target T, I want to build A and B such that its product C is such that when for any entry ij of T that is 1, Cij is big. When this is 0, this is small, and there's a gap with it. what we're gonna do actually is something stronger. I just actually we can I'm gonna generate A and B randomly, such that if the entry ij is 1, then it's gonna be big with 99%. And if this is small, if this is 0, then this is small with 99%. So it's gonna be wrong in expectation on 1% of entries. So we're gonna prove something a bit stronger.
Independent for each ij.
Yeah. Maybe no, but we don't need that. Yeah. Okay, again, just some view, like different view, that so that you really understand. Here in the matrix view, you're given T. I want to find A and B such that the product are similar in the sense of previous slide. In graph view, you can think like T encodes some directed by partigraph. And what we want to find is to find this basically two-layer graph defined by A and B, such that the max flow value from the first layer to the last layer kind of encodes matrix T. So in particular, if you look at one node I here, and you look at how, like the single source max flow value from node I, the pattern of like the value of max flow value from node I here will correspond to ith row of T, right? Okay, good. That's basically what we want to do. And let me tell you how to generate A and B. First, B is random. Like if this is B, just put an edge with probability half. That's it. That's B. Okay, so the core thing actually is in A. Okay. So how do we define A? How do we define how to put an edge to each entry to each? Yeah. Okay. And here is a way. Let's look at one node I on A. Let's say it's even like the first guy. What I'm gonna do is that I'm gonna make sure that I put that's gonna be like 20n many neighbors that I'm gonna put. The question is which one I gonna who I gonna put this edge to, but there's gonna be 20n many. Okay. And okay, there's gonna be 20n many case that I gonna put an edge here. And which k? So I choose k such that the kth row of B and the ith row of T are correlated. They look the same. So let me be clear. I'm gonna choose to put from here to K, and this edge pattern from this node K to B, this basically encode the kth row of B, right? And I'm gonna put this edge here if this pattern looks like row I of T. For example, if this is T, and then the first row of T, this is there. If this is T, and suppose that the first row of T looks like this. This is all 0, this is all 1. then if this K row of B looks like, let's say it has only edges to this guy, then it means that this K row of B is just the same as the ith row, the first row of T. If they are similar, if these patterns are similar, then I would match. Okay. But I don't actually say that they must be the same. They just need to agree on significantly more than half of bits. Okay. So this is important, like, and the trickiest part. Ask question if this is not clear.
So how do you know how do we know the B row?
I'm gonna tell you now. Oh. Okay. So if I just said that they need to agree with on n over 2 bits, this will happen with probability half, right? Because it's just random bits on B. Okay, like everything in B is random. So the expectation they agree on half. But now I just asked it to deviate from n over 2 by just root n. When you have n bits, how much it can deviate from half? That's still like, sorry, if the expectation of n random bits is like n over 2, what's the probability that the random bits that kind of you get this deviation of root n? It still happens with constant probability. So, okay. So it means that this event happen with still a constant probability. But like I choose C, like the number of nodes here is like a NC. I just choose C to be big enough. So that in expectation, like I have this many events happen, and I want this to be more than 28. So that basically I know that there are much more than something like PCN many neighbor, PCN many case, such that it's the rows here are correlated, and I could put an H2. So this is more than 20n, so I can just choose like 20n among these good guys to connect to. All right. Okay. So, okay. So again, I just put an edge from I to K if the ith row of T and the kth row of B look similar. Okay. So I put an edge from 1 to this guy. If I look at the first row of T and the pattern of how this thing looks similar to this row. And I have enough, like, just by choosing this stage to go then there are enough number of good nodes that I can choose to connect to. Okay, that's the construction. All right. Any question now? Now that that's construction, we can analyze this now. Okay. All right. So we want to prove this, right? If the entry from I to J is like on the target T is 1, then like a max flow, like Cij should be big with good probability. And otherwise, if it's 0, this should be small with good probability. Okay. So from now, like maybe just think of I as 1. I just like let's look at the first row of T. And again, suppose that the first row of T looks like this. This is 0 and this is all 1. In graph view, it's like the matrix that encode T looks like the first node here just have all edges to this thing. Okay. And we want to prove this one. Okay, let's analyze this. Consider like one entry K, okay? one node K here, okay? Such that I connect from 1 to K. The fact that I connect from 1 to K, I know that the Kth row of B is similar to the Kth row, the first row of T. It means that this thing looks like, maybe it looks like most of the edges are going in this way. Not most, but like it's correlated in a good way. Right. Let's imagine first that they are really the same and analyze what happened. Suppose that they are really the same. So for all of these K guys, the neighbor here, all these guys have the same pattern. Just have edges to the second half. Okay. Then let's see. If I choose J to be this guy, what's the max flow value from 1 to J? It's going to be 20 N, because I can just go from this guy, and then there is an edge to this guy. I can go to this neighbor, and there's going to be an edge to this guy. Every single of one's neighbor have an edge to J. Right. So there are just 20 N many paths from 1 to J through 20 N many neighbor of 1. On the other hand, if let's say J is here, okay, so among all of one's neighbor has no edge to J. There's no edge to J. So the max flow value from I to J is 0. So if the rows are perfectly correlated, you just get this gap, like perfect gap of like a 0 and 20 N. But now we just have like a some correlation, okay, where we have some bias of root N. And we just need to calculate, and we're just gonna get the same as what we want now. So like we just now have that this row and this row are correlated on like half fraction, but with some bias of 1 over root N. Okay. So it means that like if T ij is 1, if T1j is 1, 0, sorry, if this is 0, then like in expectation, this is going to be less than 20 N times this bias. Yeah. Right. Exactly. And if this is 1, now like on my 20 N neighbors, like 20 N neighbor of 1, like we can go to J with kind of this probability. So in expectation, this is like 10 N plus some root N. So that, like, so now we get the gap of root N in expectation. And the last step is just to say that this is good with, like it should be still small with 99% probability. So now we can ask, like, in expectation, this is like less than 10 minus 20 root N. what's the probability that this thing is less than, actually is more than 10 n minus root n? Okay. So you expect it to be 10n minus 20 root n. I already said that it should still be less than 10n minus root n. If not true, then it deviates from what you expect by 19 root n. That is like that holds with like a 99%, right? Yeah. So basically, we get this. Good. Questions?
So root n is the biggest function that works in the synaptic.
Yeah, like what with this technique, I get root n. Yeah. 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 Exactly. So yeah, again, we basically get this kind of picture. Given any matrix T, can factorize it so that the product looks like your target. Let me conclude. Like what you've seen is that like basically we get this additive approximation hardness of root n space. Well, in directed graph. To make it work for undirected graph, it's not really hard at all actually. But I don't think I will talk about it. Happy to talk about it if any of you want to. And here's the open thing that I will ask again. Like you see from the techniques today that root n seems like it's like a bottleneck. Can you improve it? Yeah.
Is this for unit capacity, the open problem?
Yeah, it's for unit capacity.
Isn't it the answer between 1 and n? For unit?
Oh, I mean, let's say this is like maybe like thing of like a 0.0001 n. Yeah. Yeah. Is there a connection of this technique to other things? Yeah. Like when Pasin listened to this talk, he said to me that there are so many interesting connections to differential privacy. I haven't looked into it, but yeah, but maybe there's some interesting connection, even more to something else. All right. Yeah. Thanks.
Why doesn't this work for undirected graphs immediately? Like, what goes wrong? You like send things the wrong way, I guess.
Very good. Yes. The reason that it doesn't work for undirected graph immediately is because I might, like here, I kind of look at I and J. I basically count the common neighbor. Like if this is neighbor of I and this is neighbor of J, I basically count this thing, right? But in undirected graph, I might be able to go here and then go here and here and here. That can happen. So this is kind of the noise that like you don't want to take care of. Like you don't want to count, you don't want it to interfere with your information. Now what we can do is actually this. We can make sure that, yeah, this is really rough idea how to make it work in undirected graph. We're just gonna make sure that like there's gonna be like, this is n-1 guys here. I just gonna have like make sure that there are n-1 additional disjoint path to go from I to somewhere here, to all of this guy, to exhaust all of this guy, and to go somewhere else here, and then to J. So this basically kind of before it's like the number of paths that looks like this interfere with your information. But now I just make sure that there are exactly n minus 1 additional path add to you. So this is just a fixed number. So it like I need to modify the graph a bit, but just by some simple modification, you just know that there are just this fixed n minus 1 path add to your maximum value. So it doesn't really like hurt you.
And the best you can possibly get using the matrix factor.
It's the best. I don't know. Yeah, maybe like maybe with this matrix factorization techniques, maybe there's better way. I don't have the barrier. Yeah.
Regarding your question, this connection to other techniques, so if you see the one-way communication complexity of gap having distance, basically this reduction applied to one row, like you don't have a matrix there on that one row.
I see.
So lower bound of joy and there's so reduction for proving it's conceptually similar from,
Very good. I see.
but I guess the multiplication part is
Yeah, right. Okay, then yeah, thanks. Yeah.